All right, so hi everybody. So welcome again to the Technion robotics seminars for this semester. And today we are lucky to host Dr. David Rosen from MIT, from the Laboratory for Information Decision System, leads at MIT. David is focused on mathematical foundations for machine perception, uh, trying to apply tools from different principles and disciplines to develop robust machine perception systems in a very wide sense, I guess. And we are very happy to hear David's most recent research. Okay, go ahead, David.
Okay, thanks very much. And yeah, so thanks for the invitation. It's a pleasure to be here. Just as a general statement, like I would much prefer this to be like a more conversational kind of format than me just talking for the next hour or so. So, please do, if anything's not clear, if there's any questions, like please do feel free to just jump in during the talk. Okay, yes, let's just dive right in. So this is the Technion Autonomous Systems seminar. And so, as you know, robotics is the science of physically embodied autonomous agents. And so if we think about the kinds of things that we would like robots to be able to do, the core capabilities we'd like them to have, things like planning, navigation, manipulation, all of these things, because they're embodied agents, require having some understanding of what the environment around them looks like. And so that is to say, all of these things require having accurate models of the environment to support these core capabilities. So just to set the stage a bit, if we take the example of, let's say, autonomous vehicles, what I'm showing you here is an internal representation of the external world that an autonomous vehicle, in this case, Waymo autonomous vehicle, has as it's driving down the road in, I believe, Mountain View, California. And so the main thing that I want to highlight here is that if you look at the actual models that are being constructed, the internal representation that it has, the vast majority of the complexity in the world in this model is actually due to the external environment. So it's having to keep track of things like, where are other cars, pedestrians, what lane of the road is it on, what are the rules of the road, traffic lights, and so on. And of course, if we think about, driving close to cyclists or, having to negotiate complex intersections and so on, it's obviously very important that these estimates be computed correctly, right? Because you could easily imagine that if you misclassify a stop sign as something else or fail to recognize when a light is red, for instance, that could cause really bad things to happen. So the main takeaway from this, or the thing that I want to highlight here, is that the vast majority of the modeling complexity associated with this kind of state representation is due to the external world rather than the robot itself. Okay, so all this is just to say that perception is then obviously a really important part of designing reliable systems. And so when I say perception, what do I actually mean? Well, really, when I say this, what I really mean is this is essentially the box that connects the raw sensory data that's coming off of our lasers or camera systems or whatever sensors might be on the agent, and takes that and then produces this world model that we then want to use as the basis for all of our subsequent planning. And so, just to formalize this problem a bit, if you were to open up, most papers in robotic perception or computer vision, let's say, you would see sort of a canonical formulation of this problem. And it would be formulated as a maximum likelihood estimation, or more generally an M estimation, or even more generally as a function fitting inference procedure for the most part. And so the setup for here is relatively easy to write down. We've got some raw data, which is going to be, camera images, laser scans, what have you, which is coming off of our sensors. And we want to use that data. We want to fit a world model, which in this case is going to be represented by this vector theta. So theta is going to be just the collection of everything that we care about in the world. And so the goal then is to try to come up with an explanation for this data, an assignment or an estimate of this state theta that is in some sense most consistent with the available data that we've gotten. And so we're going to do this by means of function minimization. So we're going to have some function that is going to measure essentially how well a given guess of the state of the world agrees with the data that we have. And we're going to try to pick the best one. So this, of course, is not the only way to do it, but it's a particularly attractive way of doing it for real-time operation in robotics applications, because we know how to do function optimization reasonably fast, at least local searching. Okay, so that's sort of a fairly general approach to this problem. Unfortunately, despite the fact that this admits a mathematically nice formulation, it's difficult in many instances to actually do this in practice, at least in a reliable way. And the fundamental challenge that shows up here is the fact that many of these machine perception problems that we'd like to be able to solve, many fundamental machine perception problems that we'd like to be able to solve, are both high dimensional and non-convex. And they're high dimensional because, as we saw in the previous slide, we're having to estimate a lot of different things that are all very complex objects. And so there's just a lot of stuff that we need to keep track of. And they're non-convex in many cases, in part because we have, for example, non-convex states that we're trying to estimate, things like orientations. Or we have non-convex sensing models like projective camera models, for instance. And so, for those of you who, just to make sure we're all on the same page, if you recall from your class, from an optimization course, one of the major watersheds in terms of classification of optimization problems is between convexity and non-convexity. So convex problems are easy to solve essentially because every local minimizer is a global minimizer. And as a result, in order to solve these problems, I can just pick any starting point I like, I go downhill, and as soon as I find a local min, I know that I'm done, and that I have, in fact, a globally optimal solution to the problem. This trick, and as a result, so these are fairly easy to optimize. This trick no longer works in the non-convex setting because, if I pick a random starting point and I go downhill, I'll arrive at some local minimizer, but I have no way of knowing whether or not that local one is, in fact, the globally correct solution or not. And even if someone were to just tell me that it's not, that still wouldn't necessarily help me because just knowing that this is not the right minimizer doesn't necessarily tell me how to get from here to where I want to actually be. And so the point then is that not only is this sort of practically or empirically hard, but it's hard in a formal sense. So one can easily show that this such a general modeling formulation is easily general enough to encompass problems that are known to be NP hard in particular. And so as a practical matter, this manifests in the form of lots of really bad suboptimal local minima.
Quick question.
Yes.
Sorry, theta here is continuous or can be also discrete?
Oh, good question. Yeah. So for the purposes of this talk, I'm focusing primarily on the continuous case, although certainly one can add some additional complexity in here via discrete or combinatorial variables too. Although interestingly, one sort of natural way of solving those is exactly to take continuous relaxation and then do some various approximations on top of it. So yeah, good question. Okay, yeah. So you might say, okay, well that's all well and good, Dave, but how much of an issue is this in practice actually? Because people in deep nets, for example, solve non-convex problems all the time, and it doesn't really seem to be that big an issue. So just to convince you that this in fact is an issue for many of the problems that we care about as roboticists, at least, what I'm going to show you here is a real data set. So this is a data set that was collected by the Stanford autonomous car as it was exploring this multi-level parking garage. And so what you're going to see here is it's going to leave this bottom left parking lot. It's going to drive inside the structure up and down the. And so the goal here is to estimate, construct an estimate of the trajectory of this vehicle. And so if you were to look at the correct trajectory, this is in fact the true global minimizer for a particular estimation problem that's formulated in this way. This is what it would look like. And so you can see exactly the path that it took. You can identify all the parking ramps and so on inside this structure. Now, okay, so this is the optimal estimate. Now, if we apply this kind of local search technique, which is just generic gradient-based optimization, what are the kinds of things that we can get out of a local search procedure applied to these kinds of non-convex problems? Well, what you'll find is that if you pick a bad starting point, what you will get are things that look like this. And so I hope it's fairly clear from this that if you try driving your autonomous car through a parking garage or on the Autobahn at like 90 miles an hour or something, and you have estimates that look like this, that's going to be really bad. So in fact, and part of this can be explained by the fact that in many cases, in contrast to like machine learning applications, in many instances we are actually not operating in the high data regime. And so a lot of the sort of smoothing of the optimization landscape that occurs in those data-rich regimes actually doesn't happen in these problems. And so one can sort of view this as an instance of that general phenomenon. And we'll see examples of that in a little bit more detail later in the talk.
How much does this depend on the model that you're using? So for example, you can represent angles using, I don't know, quaternions or whatever. Is this
so that is an excellent question. I'm going to speak about that specific point in a few slides. Yeah, so I'm going to come back to that. Okay, so the overall motivation or the overall idea then is that given these considerations, what we're really interested in is can we develop tractable perception algorithms that are fast enough to be run on resource-limited mobile platforms in real time, that also come with some kind of actual performance guarantees, so that we feel confident in applying them, especially in safety and life-critical applications like autonomous vehicles. Okay, so the main thesis, the main punchline that I want to convey in this talk is that one particular way of doing this is through the use of convex relaxation, and in particular semi-definite relaxation strategies. And so what we're going to show in this talk is that semi-definite relaxation in particular provides a powerful approach for building both fast and reliable machine perception systems. And so in particular, we can show that for a pretty general set of interesting, practically relevant problems, it is actually possible to show that you can provably recover optimal solutions by means of this process to generally intractable estimation problems under realistic operating conditions. And that we can do this with a speed that is comparable to existing or previous state-of-the-art heuristic local search techniques. And so the payoff for doing that is that this is going to give us both a practical and a principled approach to building robust machine perception systems. So just as a general outline for the rest of the talk then, I'm going to be using robotic mapping as a running sort of canonical example here because it's a good representative. It's nice in that it admits a relatively nice mathematical formulation, so it's easy to sort of reason about. It's rich enough to capture a lot of interesting phenomena that sort of really highlight the challenges that are involved in the design of methods like this. And also just because, historically it was one of the first problems that this class of techniques was developed to solve. And so I'm going to give you sort of a lightning introduction to postgraph-SLAM for those of you who may not be intimately familiar with this. And then I'm going to show what the design of a technique like this looks like in that specific context. So I'll show you how one can derive a semi-definite relaxation for that specific problem together with a fast optimization method for solving it. And the combination of those two things is going to be a method called SE-Sync, which is a certifiably correct algorithm for SLAM, meaning that it's capable of finding globally optimal solutions to this generally intractable problem under reasonable operating conditions. And then it can verify that the answers that it gets are in fact the correct ones. And then at the end, I'll describe how one can take this general approach that we sort of considered in this running example and broaden this out to encompass a fairly broad set of estimation problems, and then discuss some open problems and future research directions at the end. Okay, so as I said at the beginning, robotics is the science of physically embodied autonomous systems. We want to be able to understand, what the environment around us looks like, and one of the most basic features of the environment that we might be interested in recovering is the geometry. And so, in particular, if we want to be able to drive robots around without bouncing off walls and stuff, we're very interested in knowing what the actual geometry of the environment looks like. And so, a key question then is, how specifically do we acquire these geometric models that we want to use for planning and navigation, let's say. Okay, so if we consider a concrete example of this, let's consider a robot exploring some initially unknown environment, like let's say this data center. So we're going to have some drone, we're going to release it inside this building, and it's going to fly around, and we'd like it to reconstruct a map. And so, it's going to, as I said, it's going to fly around, it's going to go through some trajectory here, and the first thing to notice about this is that due to limited sensing range and the fact that laser scanners and cameras only work within line of sight, at any one moment, this vehicle is only able to actually capture a small section of the environment. And so the raw information that actually comes off of the sensors themselves are little sections or segments of the environment. So we get the raw output of this is just a jumble of individual laser scans. And so, of course, if we actually knew, if somebody just told us the actual set of poses, that is, positions and orientations that this vehicle had traversed as it was exploring this environment, we could think about taking each of these scans and attaching it to each of these poses to sort of unfold this jumbled collection into a coherent representation of the environment. Excuse me. Now, unfortunately, there isn't actually a sensor that will in general tell us this. So for example, GPS doesn't work indoors, and even when one has access to GPS, you still actually need to know what your orientation is in order to be able to do this. And well, that's problematic. And so we might say, okay, well, how are we going to solve this problem? So one thing that you can do is you can observe that, if I see a feature in the environment, like a sign or a table or a chair or something of that sort, and I see that same object in two different scans, the apparent motion of that object between those two different scans conveys some information about how my vehicle must have moved between when those two scans were taken. And so what I can think about doing then is searching over my data set or my individual set of scans for common objects or common landmarks that I can use to then generate noisy estimates of the relative motions between these positions and orientations. And by doing that, I can then think about building up this network of noisy spatial relations. And if I can then estimate a set of poses that is consistent with those pairwise relative relations, this gives me a way of backing out what this trajectory must have been from my raw data. And if I can do that, then I can do this process that I mentioned before, where I can unfold these scans and generate my map. So this is the main idea behind how a lot of these mapping systems are constructed. And so we can formalize this using an object called the pose graph. So this is just a graphical model. And so it's it's a directed graphical model that models the joint distribution of all of these scans that I got, or all of these noisy relative measurements, as a probabilistic model. And so the vertices in this case correspond to the unknown poses that I want to estimate. The edges correspond to these pairwise noisy transformations that I've referred to before. And we're going to assume that each of these noisy measurements comes from a probabilistic sampling model. And so we can so this then gives us a probabilistic graphical model formulation for this underlying problem that we want to solve. And so then the postgraph SLAM problem is exactly what you'd expect. So somebody's going to give us one of these postgraph SLAM models that models this noisy network of spatial relations. And what we want to do then is to come up with the estimate, the assignment to these unknown positions and orientations that is most consistent with these available measurements. So this is just a very standard approach. We're just going to use standard maximum likelihood estimation in order to do this. And so the point that I want to, by the way, any questions on any of this so far before I proceed? Nope. Okay. Okay, excellent. So, so the point that I want to make then is that this is exactly an instance. Oh, sorry. So this problem turns out to be, ubiquitous in geometric estimation. Perhaps it's not surprising because this is really a problem about co-registering data together. And so it's not surprising that you'd expect to see this come up in a lot of geometric estimation problems. So it's ubiquitous in robotic mapping, as we just saw. It's the basis of bundle adjustment or 3D visual reconstruction. This also arises as a core part of a sensor network localization. And certain special cases of this also arise as problems of independent interest, such as rotation averaging in computer vision, or even community detection for those who are more interested in like information theory and so on.
So that the data station is given to you, right?
Yeah. So for the purposes of this talk, I'm just assuming that we have known data association. Yeah. But yeah, obviously that's a whole that is a significant problem as well. And actually, I'll come back to this at the end, but there are extensions of this to try to address that as well. Okay, so the main takeaway from this is this is a relatively concise, mathematically concise or elegant problem that we can write down, but it's rich enough to encompass a lot or to address a lot of the problems that are really practically important. So a couple of other things. I also want to point out this is exactly an instance of what we saw before. We're fitting some model by minimizing some loss function here. And as we saw before, this is a high-dimensional non-convex problem. And it's high-dimensional in part because every time our robot moves, we're introducing another variable whose state we now have to estimate. And it's non-convex in part because we're having to estimate orientations as well. And so the configuration space, the actual space in which our variables of estimation live, is itself already non-convex. And so, as we saw before, this is exactly what leads to the presence of these many suboptimal local minima. And so the main question that we're going to try to address throughout the remainder of this writing example then is how can we ensure the recovery of good SLAM estimates given these considerations? Okay, so I'll just jump right into the main idea. So it turns out, it's not too hard to show that that postgraph SLAM formulation that I showed in the previous slide is itself an NP-hard problem class. And so we should not expect that we will be able to solve a problem like this efficiently in general. Now, so the key observation, however, is that the word in general is doing a lot of work in that previous statement. And so, maybe we don't actually care about solving every conceivable possible instance that one could write down for postgraph SLAM. Maybe it would be enough, thinking about our engineer hats for a moment, maybe it would be enough to just approximate or well approximate a set of reasonable instances that we actually happen to care about in practice. And so the intuition behind this is that really what NP hardness refers to is it's a worst case notion of complexity. And so your problem is NP hard if for any algorithm that you give me, I can go into my problem space and I can pick out sort of one bad example at least. But that says nothing about sort of average case hardness or what a reasonable problem instance might look like. And so from an intuitive standpoint, if we are having to solve these estimation problems just because we have sensor noise, then you might hope at least that if nature is not actively out to get you, if it's not adversarially conspiring against you, and in particular, if we're trying to design sensors that are accurate because we're engineers, then one might hope that if the noise on the data that we have is not too bad, then perhaps we might be able to draw a diagram that looks like this, in which the set of real world cases that we actually care about is separated somehow from this set of hardcore cases that make this overall problem class actually NP hard. And so you can imagine then that if our problem space looks like this, then perhaps we can do better on this subset of cases that we care about than what this NP hardness result might suggest. And so now you might say, okay, well, that's great as far as it goes, Dave, but like, how do we actually do that? How do we actually take that and make it operational? So what we're going to propose in this talk is to use convex relaxation specifically as a means of doing that. And so the basic idea behind this, for those of you who may not have seen this before, is that we're trying to solve a problem which is hard because it's non-convex. And so what we can do is to think about approximating our original hard problem with a non-convex approximation that we will solve instead. And the hope or the goal, what we would like to have, is that the minimizer to that non-convex problem, which we can solve globally, will then be in some sense close to the solution for the original problem that we're trying to approximate. And so that's the main idea. And so this is kind of a nice, there's some nice properties that this approach has. So two main ones that I want to mention here. So one of them is that this is kind of nice from an algorithmic standpoint, because in many instances there are standard machinery for constructing these. So things like Lagrangian relaxation, adder approximation for, let's say, combinatorial problems that you might have seen before if you're familiar with certain of these optimization techniques. So that's point number one, is that there's sort of a nice mechanical way of doing this in many cases. And the second point is that because convex programs are much easier to analyze, certainly globally, than their non-convex counterparts, it's oftentimes possible to actually prove some formal guarantees on the quality of the solutions that these approximation methods find. And so as a result, we have sort of a nice mechanical means of generating these approximations and actually being able to say in certain cases, provide performance guarantees for them, which is not necessarily something that one can do in the purely non-convex case. So this is the main idea that's going to underpin the rest of our development. So any questions on this so far?
Yeah, I've got a question. I'm not sure I understand the jump from talking about real world cases versus hard cases to making this relaxation, because it's a different thing, right? You're not making assumptions on what the problems looks like and then solving this special case, right?
Yeah, sorry, maybe I should be more precise. The intuition here is that even if I'm using an approximation, if the answer to my problem, if I'm in a regime where the solution to my problem is in some sense easier or more obvious, then even though I'm using an approximation, the hope would be that this approximation is still quite sharp. So that's sort of the connection between this jump. Does that make sense?
Yeah, I mean, maybe you'll come to that, but can you say something about what are the assumptions that you need to make about what the real world looks like in order for this to actually work well?
Oh yeah, okay. Yeah, I'll give some sharper statements about that coming up.
Okay,
yeah.
All right.
Okay.
Thanks.
Yeah. Okay, so what we're going to do for the remainder of this section then is I'm going to show you how you can take that sort of pictorial diagram and actually operationalize it as applied to this post-Grabstein problem. So the first thing we're going to need to do is we're going to need to come up with a specific observation model for the measurements that we're going to be using as the basis for our algorithm. So we're going to assume the following observation model. So we're going to assume, our measurements are relative transforms, they're relative positions and orientations. And so we're going to assume that we have additive Gaussian noise on our translational estimates, which is fairly standard. We're going to assume multiplicative Langevin noise for our rotations, since this is a Lie group. So for those of you who have not seen this before, the Langevin distribution is an exponential family distribution on the set of orientations. This is just a PDF for it. And if you haven't seen it before, that's fine. It actually admits a relatively nice geometric description in the 2 and 3D case. So to draw a sample from this, what you would do is you would uniformly sample a rotation axis from the sphere. And then you would independently sample a von Mises distributed rotation angle around that axis. So this is I'm showing here a PDF of the von Mises distribution on the circle, just in the bottom right here. And the key thing to take away from this is that this actually is asymptotically looks like a Gaussian if your noise is relatively concentrated. And so the point here is that this is not the distribution on rotations that you would typically see if you look in a standard robotics paper. But it asymptotically reduces to the same thing for if your measurements are reasonably precise. So that's point number one. And point number two, the point that I want to emphasize that underpins this choice is that this is an exponential family distribution that has a nice linear objective inside the exponential. And so for those of you who have not seen these before, just as an aside, exponential family distributions in information theory and statistics are a big deal. And they're a big deal in part because they lead to algebraically nice formulations for maximum likelihood estimators. So there's a question earlier about how do we choose our models, for example, or what is the significance of the model selection? This is one point that I wanted to explicitly emphasize was that this is a useful modeling assumption because it's it's a maximum likelihood distribution, so it's a reasonable thing to do. Excuse me, maximum entropy distribution. But B, more operationally or pragmatically, this particular formulation leads to a nice maximum likelihood estimation, and in particular, a maximum likelihood estimation that has a convex quadratic objective.
I assume that your formulation is also relevant for other observation models, such as, let's say, monocular cameras and stuff like that.
Yeah, so I'm going to be focusing on this particular one for the purposes of this talk, but I will come back to that at the end and sort of speak a little more about that. Yeah. Okay, so what I'm going to show you now is sort of how we actually generate this relaxation for this particular problem. So we're going to need to do one quick sort of minor manipulation in order to get there. What we can do by looking at this is we'll notice that if we fix the set of rotations, the rotational estimates, then what this problem reduces to is just optimization over an unconstrained nonlinearly squares optimization, which we know how to solve in a closed form. And so what we can think about doing then is actually just solving analytically for the optimal values of our translational states as a function of our rotations. And if we do that, we can then take those optimal assignments, we can write t as a function of r and just plug it back into our original objective. And if we do that, what we get then is a simplification of this problem in which the translations have just been analytically eliminated. And so it's completely equivalent to the original problem, but it's now an estimation that is just over orientations alone, as opposed to orientations plus translations. Okay, so this is just a simplification that's going to help make some of the subsequent stuff that comes up next a little bit easier. Okay, so this is the main step then. Here's where we're going to generate our actual relaxation. So we saw before. So the only non-convex part of this problem now is this constraint that's on our state variables. So the fact that these have to lie in a non-convex space. But what we might notice is that these actual variables, these rotation variables, are this block matrix of rotations. Only actually enters our problem through this outer product R transpose R. And if we think about what this looks like, well, it's going to be a positive semi-definite matrix because it's an outer product of two things. And it's going to have ones along its block diagonal because these are all rotations and R transpose R equals the identity for a rotation matrix. And so, every one of our feasible points then is going to lie inside a set that looks like this. It's going to be the intersection of a positive. It's going to lie in the set of matrices that are positive semi-definite and have ones along their block diagonal. And the interesting thing to note about this is that this set is what's called a spectrohedron. It's the intersection of the positive semi-definite cone with a linear subspace. And the positive semi-definite cone is a convex set, and so are linear subspaces. And as a result, this is the intersection of two convex sets, and so it's convex. And so what we can think about then...
David?
Yes?
Can you explain what is Q tilde Q here?
Oh, sorry. Tilde Q is a data matrix. Sorry. Yeah. So this is just it turns out that if you look at this formulation, this is as I said before, this is a convex quadratic program. The objective is rather, and so you can parameterize this just using a positive semi-definite matrix Q, which is just constructed directly from our original measurements.
So Q is positive semi-definite.
Yeah, and it's parameterized by the problem data, or it's constructed directly from the problem data, I should say.
Thanks.
Yeah, thanks. Does that answer your question? Is that clear?
And can you also say where does the assumption on the noise come into here?
Oh, I haven't gotten there just yet. That'll come up in a little bit. Yeah. So I mean, the assumption of the assumption of those particular distributions that I said leads to this particular optimization problem as the maximum likelihood estimation.
Okay.
But the condition about boundedness on the noise I haven't gotten to yet. Okay, yeah. So the point here then is that what we've shown is that every feasible point for our original problem belongs to this set C, which is a convex set. And so what I can think about doing then is replacing every instance of my original variable R, or R transpose R rather, with just a generic positive semi-definite matrix that has this correct block diagonal structure. And so the advantage to this is, what this inclusion means is that we can regard this problem on the right as being obtained by just expanding the feasible set for our original problem. And so what we'll notice is that the objective in both of these is exactly the same. In particular, it's a linear objective in this expanded form. But the feasible set here is now convex. And as a result, this is actually a convex problem. It's a convex relaxation, in particular, a semi-definite relaxation of our original problem. And so this is a mechanical way of generating, in this case, a semi-definite relaxation for original post-graph slam problem. Is that clear, this construction? Or is anything about this not clear, I should say? Okay, great. So this is nice, and there's a couple things that you get immediately from having done this. So the first is that it's immediate that the optimal value of this SDP is going to be a lower bound for the optimal value of our original problem. And that's literally just because we got this relaxation by expanding the feasible set. And so we're always going to be able to do at least as well in terms of minimizing the function value because we just have more choices to pick from. And so that's pretty clear. A second, more interesting observation is that if it so happens that I solve this relaxation and the minimizer that I get happens to factor in this way, then it's also immediate that this R factor, so if it factors in a way like this, where R is feasible for my original problem, then it's immediate that this R is actually a globally optimal solution. And that comes directly from the fact that if I just plug this R into my original problem, it attains an objective value that matches this lower bound, which just serves as a certificate of optimality in this case.
This is globally optimal with respect to the simplified problem or the original one?
So they actually have the same objective value. So yeah. The same optimal value, sorry, I should say, yeah. Okay, so you might say, okay, well, that's great as far as it goes. But given there's a bunch of extra points that you've added in this expansion, why would you ever actually expect this to occur? And so the main result that we proved in our original paper on this is, in fact, this actually does occur. So this is a bit of a mouthful. So let me sort of walk you through what the statement of this result actually is. So the way to read this is Q under bar is the data matrix for this problem that is constructed from the noiseless, that is the ground truth relative measurements. And so what this result says is that for each realization of this problem, for every set of ground truth assignments, if we knew, if somebody gave us what the ground truth data matrix was, then there's going to be some constant which is a function of that ground truth matrix, such that if the noisy version of this matrix that we actually got, the actual version of this matrix that's constructed from our noisy measurements, is not too far away from its ground truth realization, then this semi-definite relaxation is going to have a unique solution. And that solution is going to factor in exactly the way that we require in order to produce a global minimizer for our original non-convex problem. And so these two things together imply that we can actually numerically solve this SDP, and from that solution obtain a globally optimal solution to our original problem, provided that the noise on the data is not too big. Okay, and so this is sort of the main result that is going to justify the algorithmic approach that we're gonna adopt.
Can you give an intuition to why this holds?
Yes, so I'm gonna get to that right now. In fact, actually, yeah. So unfortunately, I can't give you the full explanation in this short talk, but I want to at least give a high-level sketch, or at least a brief intuition for why one might hope that a result like this should be true. So the main idea behind this is we're going to exploit Lagrangian duality. So we started with our original post-graph slam problem. One can show that you can, by relaxing the determinant constraints on the orientations, that one can derive a Lagrangian dual from that looks like this. The dual of this dual is actually the problem that I showed on the previous page. So that was not originally, the argument that I showed you in the previous slide was not originally how we derived this. It's a little bit more concise for explaining it the way that we actually got this via Lagrangian relaxation. And so the main insight here basically then is to exploit the relation between the variables in these problems in order to say something about optimality. And so in particular, because the set of rotations, the constraints that appear in this problem are relatively nice, it's actually possible to write down for our original problem what the Lagrange multipliers corresponding to a solution have to be in a closed form. And so if you think back to Lagrangian duality, for those of you who've seen it before, these dual variables, these Lagrange multipliers for our original non-convex optimization problem are closely related to the decision variables that appear in our Lagrangian relaxation. And similarly, this Lagrangian dual, because it's a convex program itself, has a dual, which is also a convex problem, which is the one that I showed you before. And so you might say, okay, well, it seems like the variables for each of these should somehow be closely related to each other. And indeed, we saw in the previous case that these z's actually kind of admit a natural interpretation of sort of generalizations of R transpose R in our original problem. And so what we can do then is, because these are convex, we can write down, if we know that we're looking for a solution that looks like this, we want to recover this solution from our convex problem. We can just write down what the KKT conditions are, which are both necessary and sufficient for convex problems. And we can just see what they look like. And it turns out that if you write down what the KKT conditions would look like for an assumed minimizer that looks like this, it turns out that they reduce to they involve a certificate matrix which looks like this. So it's your data matrix minus these Lagrange multipliers. And the condition that we need to hold is that this matrix has to be positive semi-definite.
Wait, and so Q tilde here is the data with the noise, right? The noise.
Yes. Right. Yeah. And so the two things that sort of the two main insights that one needs to show this then are it's not too hard to show that this condition always holds in the noiseless case. That's fairly easy to show. And from an intuitive standpoint, it's maybe not totally crazy to expect that something like this might be true, in part because again, this is a statistical estimation problem, right? So somehow, if somebody gave you perfectly noiseless data and you cannot recover the ground truth solution given perfectly noiseless data, that somehow is an indication that maybe your estimation problem should need some serious revision, right? So somehow, it's not too hard to convince yourself that one might hope that these problems are easy in the noiseless case. So it's not too hard to show this. And then the key observation is that for any sort of reasonable statistical estimator, you would want to see that your estimate, your minimizer, should go to the ground truth as the noise goes to 0. And since this certificate matrix is a function of both the data matrix itself and also your minimizer, if both of these are going to their ground truth values and the eigenvalues of the matrix are continuous functions of that matrix, then the main idea is that sort of underlies this argument is that by continuity, we can control the certificate matrix into remaining positive definite by just preventing it from getting too far away from this ground truth state by controlling the noise on the data. Okay, so this is just a sketch. I'd refer you to the paper for the details, but I hope at least that this conveys at least a sense of sort of the main arguments that are used in the proof.
Wait, what do you mean by controlling this term, this distance metric? What does it mean?
Oh, sorry. So this is where the assumption comes from. Essentially, what I'm saying is that if I force this to be sufficiently small, I can guarantee that this.
Yeah.
Sorry.
How can you manipulate it? Because this is the data that you in practice get, right?
Oh yeah, but I'm saying that's the condition though. So the condition is certainly this is not going to work for every problem, right? So the condition is that if I assume that my data my noise is sufficiently small, then that will guarantee that this works, right? So that's sort of the mechanism by which we do it. Okay, so that was a lot of math that I just threw at you, but just to sort of recap, so the story so far then is what we've shown is that we can derive a convex relaxation for this particular problem, and that we've proved that this relaxation actually gives you the exact answer for sufficiently small noise. And so now all we have to do is just solve that relaxation. And so you can try sticking this into your computer, and if you do that, it will crash your machine. and I know this because that was the first thing that I tried. So what I'm showing you here are some examples of trying to optimize this STP or solve this STP using some standard off-the-shelf methods. And so what I'm showing you on the bottom here is solving this problem for a simple cubical data set. So the sizes here are the number of poses that are in this small example, cubed, of course, because it's a cube. But the thing to note here is that these would be considered relatively small problems. We're only going up to, I think, a few hundred poses in this case. And this optimization is already taking several thousand seconds to solve. For a real world application of this, we would need this to be somewhere in the range of order of magnitude a second or less. And so what this is showing you is that using standard off-the-shelf methods is not going to be sufficient to get us to where we need to be in order for this to be a practical technique. And so we might say, okay, well, why is this happening? Why is this as slow as it is? And the key observation here is that we got this by sort of optimizing over a generic dense positive semi-definite matrix. And if we think about what the size of this is, I mean, a general STP matrix is of order n is going to have dimension n squared, because we have to estimate everything in the upper triangle. which means that, if I want to write down the Newton system for an optimization problem like this, that's going to be order n to the fourth, and therefore solving a system of that size using, let's say, direct matrix factorization is going to have n to the sixth cost, roughly speaking. And so if you start looking at some of these numbers, it's maybe not surprising that you start to see some of the, some fairly expensive operations happening here. And so this doesn't look good on its face. But we can actually play a similar game here to what we did before, where we say, okay, well, maybe, we don't actually care about solving every, maybe we don't care about having a generic STP solver. Maybe we can build a specialized STP solver that is adapted to the structure of this particular problem or closely related problems, let's say. And so what I'm going to show you now then is sort of how we can take advantage of some problem structure here to solve these things really fast. Okay, so the main idea behind this is we just proved in that result that I showed you a few slides ago that we expect these problems to have generically low-rank solutions. So we'll have a solution of exactly dimension d when the relaxation is exact. But even in the cases where the relaxation is not exact, it still will generically have a solution that's not too much larger. So maybe 4 or 5 instead of 3. And so there's very beautiful sort of classic result, which is due to Bieter and Montero, for solving problems that have this structure. And the main idea is we can just replace Z with a low-rank factorization of the form Y transpose Y. And so, we're just going to replace Z with these outer products that look like this. And so this has a couple of advantages. First off, it makes the semi-definiteness constraint redundant again, because every matrix like this as an outer product is positive semi-definite by construction. So we can get rid of the PSD constraints, and we're left with just a standard nonlinear program. It also has the advantage that it's much, much lower dimensional than Z itself, particularly if R is much, much less than the dimension dn. So this is going to be R by dn as opposed to dn by dn. And as a result, it's going to be much more efficient to both store and manipulate these matrices and to run optimization on the search space. And then it's not too hard to show that as long as we pick, so this rank R is going to be a free parameter, but it's not too hard to show that as long as we pick this rank to be large enough that we can represent a low rank factor for a solution to our original problem, then the minimizer of this problem will exactly be a low rank factor for the minimizer for original STP.
Do you know ahead of time what is the rank of Z star?
We don't, but I'm going to show you how you can account for that. Okay, so one other quick minor exploitation we're going to do here is if we look at the form of the constraints that we get after we make this substitution, what we'll notice is that, again, if I'm thinking of these things as being block matrices, so Y has D by R, R by D blocks. It's laid out as a row matrix. So if I think about this block diagonal constraint, what this is equivalent to is the statement that each of these blocks of Y has orthonormal columns. And it turns out that this the set of matrices that satisfy this actually form a smooth manifold called the Stiefel manifold. And as a result, what I can think about doing then is just rewriting this problem instead of being a constraint optimization problem where I'm explicitly enforcing these constraints with Lagrange multipliers or something. I can just treat this as an unconstrained optimization problem where I'm just optimizing over this smooth manifold as opposed to an extrinsically constrained problem. And so that's just going to let us solve this a little bit faster because we don't have to worry about enforcing constraints or computing extra Lagrange multipliers and stuff. Okay, so you might say, okay, so that sounds great so far, but if you look at what we've actually done, we started with the simplified pose graph problem. We produced from it a semi-definite relaxation, which was convex, and so we could solve it globally. But we observed that this was expensive enough that we can't do this directly. And so we made this assumption about assuming these low-rank factorizations again. And so if you stare at this process, you might say, okay, well, it looks like we've just replaced sort of one difficult convex, non-convex optimization problem with another slightly modified, difficult convex optimization problem. So what have we actually gained by doing this? So the key result that justifies this approach is a very beautiful proposition from Bumol, Vorninsky, and Bandera. And so what they proved was that for these kinds of Bieter-Montero factorizations of semi-definite programs, if I find a point for my rank restricted problem that is a second order rank deficient critical point, so that is, the Hessian is positive semi-definite and Y is rank deficient as a matrix, then Y is both a global minimizer of this non-convex problem. And the corresponding Z that's gotten from these factors is a globally optimal solution to this semi-definite relaxation. And so what this gives us then is a way of recognizing when local solutions to these nonlinear programs here are actually globally optimal. And so as a result of that, what we can do then is think about actually directly searching for low rank factors to our STP solutions by solving these rank restricted nonlinear programs.
At what point do you return to the original post-line problem with translations? Because here it is pure rotations, right?
Here's pure rotations, yeah, but we know exactly how to extract the translations from the translations. Yeah, we should before that it's just a linear solve, right? So our algorithm actually just operates all the way through with rotations until the very end, where we just pull out the translations at the end.
And the claim is that globally optimal solutions for pure rotation problem is necessarily the same for the more general problem?
Sorry, can you say that one more time?
So you refer here to globally optimal solutions of the pure rotation problem. Only rotations, right?
Right.
And the claim here, I guess, is that these are necessarily the globally optimal solutions also of the original post-line problem with translations.
Oh yes, yeah, and that was the sort of that derivation that I showed you way back at the beginning about just doing the analytic elimination. Yeah, they're exactly the same. Yeah. Okay, so this main idea then. Sorry, I'm gonna sort of wrap this up soon. Yeah, so these so the point here basically is that this gives us a way of recognizing when a local solution to these rank restricted nonlinear programs is in fact globally optimal. And so what we can think about doing then, so this leads to a very simple algorithm called the Riemannian staircase. And the basic idea is all we're going to do is we're going to pick our favorite starting point, y. We're going to pick some initial rank, let's say d. We're going to pick some initial starting point, say y, on the Stiefel manifold. And we're just going to apply a second order local search method, just our favorite local optimizer, to find a critical point for this problem. And then all we have to do when we're done is just check the rank. And if the rank is less than r, then that previous theorem shows us that this is a globally optimal solution and we're done. And if it's not optimal, then all we need to do is just increase the rank by 1 and just try again. And it's not too hard to show that this is going to terminate finitely, because if I go up to dimension n, then beyond that, any matrix that I get is going to be rank deficient. So this algorithm is guaranteed to terminate. But what we're going to see empirically is that it terminates in many cases considerably faster. And so the main thing that I want to call out here, though, is just that if you look at this algorithm, the only real thing that's being done here is just standard second order local search, exactly the kind that we would be doing in, let's say, traditional post-graph optimization. And so what this gives us then is a way of using all the machinery that we have for doing fast local optimization already for postgraphs, and essentially upgrading this to something that will actually enable us to recover globally optimal solutions. Okay, so to wrap this up then, putting all this together, what we get is an algorithm that we call SE-sync, and it solves these postgraph line problems by means of this procedure. So the main idea here is just we're going to start with a low rank. We're going to find a low rank factor y using our second order Riemannian staircase. We're going to use this low rank factor to compute a lower bound on this STP optimal value, which is a lower bound for our original problem. We're just going to round y to a feasible point for our original problem, because these y's might be higher dimensional. And we can do that using just a singular value decomposition. The details of that are in the paper. It's not a particularly important step, but the main idea basically is we can just use an STVD to extract from this a feasible point for our original problem. And then we're just going to return this rounded estimate together with a lower bound. And so what we show in the paper, it's not too hard to show, is that the claim here, the payoff here, is that in the event that this relaxation is exact, it's not too hard to show that this procedure that I just described, the R that returns will in fact be a globally optimal solution to this original problem. And if I just plug this R into my original objective value, in the event that this is globally optimal, if I just plug it into my original objective and compute its value, the objective value here will be equal to this lower bound, which will then certify the optimality of this solution. And so the point here is not just that it recovers optimal solutions, but it recovers both optimal solutions together with a certificate of optimality so that we can recognize when we have an optimal solution or not. Okay, so that's the main.
I have a question. Yeah, it's like it's a worst case question, right? So what would need to happen for this to return like a completely wrong solution? Like your termination condition holds, but there really is so much noise in the real world that you get something completely wrong.
Oh yeah, I mean, so it's actually not too hard to break this just by adding ridiculous levels of noise to it. So I mean, if you start connecting things in the post graph together that should not be connected together, right? Then this will definitely break the exactness. Yeah.
Okay. Thanks.
Will you be able to identify this case?
Yeah, and in fact, that's why the certification here is such a big deal, right? Is that you can directly see that from the output that these two things are not the same, right? And so you can distinguish then correct from incorrect answers, right? Which is, I think, one of the reasons that this is so useful. Okay, so just to give an example of what this looks like, just because there's been a lot of math that I've thrown at you. So what I'm going to show you here is just optimization of a sort of standard Postgraph SLAM example. So what I'm showing you here is the lowest level of the Riemannian staircase, started from a random initial configuration. So the sequence of iterates that are being shown here are exactly what a standard local Postgraph optimization method would produce if started on this data set with that initialization. And so the thing that I want to point out to you here is that, so this is roughly the last iteration at this lowest level 2. So this is the answer that a standard Postgraph SLAM method would have returned if started on this in that configuration for this problem. What we're going to see in the next step is when running this Riemannian staircase, when we do that optimality check, this SE-sync algorithm will recognize that this is not, in fact, an optimal solution, and it will augment the rank, so it'll go up in dimension. And in so doing, that'll give us just enough wiggle room, so to speak, in this higher dimensional space to escape from this suboptimal local critical point, and thereby arrive at a correct global minimizer for this problem. So this is sort of just a simple graphical illustration of what this overall procedure looks like. Okay, now some more quantitative results. So we saw before that there was this question about how much noise can we tolerate with this method. And so what I'm going to show you here are some simulation studies just to try to characterize this a little bit more concretely. So what we're going to do is we're going to vary the rotational and translational measurement precisions and also the sizes of the problems that we're considering here. And what we're interested in is how does the tightness and the computational complexity vary with these parameters? When we compare this against Gauss-Newton using a standard chordal initialization. So what I'm showing you here on the vertical axes are the relative suboptimality bounds. So remember that our method returns both a point whose objective we can evaluate together with a lower bound on the optimal objective value. We can measure then the relative difference between those two values. That is the objective value that my return point achieves and the lower bound. And what we want is for that to be super tiny because when those things agree, that means we have an optimal solution. And so the point here basically is that if you look at how these relative suboptimality lower bounds vary as a function of both angular noise and translational noise, what you see is that these are essentially flat. You'll notice that all the scalings here are roughly 10 to the negative 13, 10 to the negative 15. And so what this means then is that for these cases at least, this method is recovering globally optimal examples across these range of variations. And so the point that to emphasize here is that this is up to like 20 degrees per measurement. And if you think about the accuracy of most laser scanners, camera systems, et cetera, most of them are have angular errors that are on the order of 1 or 2 degrees, let's say, as opposed to 10 to 20 degrees. So the punchline here is that the actual practically tolerable level of noise is way beyond what we would expect to see for typical robotics applications. Yeah, similarly, we can consider how does the computational cost of this scale with both noise and problem size. So what I'm showing you here are now computational cost in terms of seconds. And this is comparing our SE-sync method against a dogleg or a Gauss-Newton type method that is implemented in GTSAM. And so again, the point here is that because we have taken advantage of the specific geometry of our problem's feasible set in this case, not only can we recover globally optimal solutions, but we can do it actually faster than these prior methods, prior state-of-the-art methods, by being a little bit more clever about how we set up our optimization algorithm. And then of course, the final check is of course real-world stuff, right? Because everybody, you might say, okay, that's great, Dave, but simulation is doomed to succeed. How does it work in the real world? So these are results for large-scale real-world benchmarks, SLAM benchmarks. This is real data that was not necessarily sampled from the generative model that I showed you earlier. But the same conclusions here hold. So what I want to highlight here is, we're achieving global optimality on all these tested examples. These are large enough that they are certainly representative of what would be considered large-scale real-world problems. And again, we see that we're recovering these at a computational cost that is comparable with prior state-of-the-art methods. Actually, less than prior state-of-the-art methods, again, because we are careful about the design of our optimization technique. Okay, so to summarize then, what I've sort of highlighted in this particular talk was the design of a certifiably correct method for the particular case of Postgraph SLAM. So we call this SE-Sync, and as we showed before, this is something that recovers globally optimal estimates for moderate noise, typically up to like 10 times what you typically expect to see in robotics applications. And it's significantly faster than prior state-of-the-art techniques. And so this is actually the first practical algorithm to appear in the SLAM literature that is provably capable of recovering correct solutions to this fundamental estimation problem. And so in fact, this particular technique actually resolved what had been an open problem that originated in the work of Lou and Milios in the late 1990s on the reliability of SLAM systems, in fact. And so if that had been sort of the end of the story, I would have been fairly, I'd have been happy with that. But the reason that I am really excited about this technique is not just about what it says about this particular problem, but about what it says about our ability to design reliable estimators more generally. So the key observation, this is one of the things that we talk about in the paper, is that there's a natural way of taking the relaxation approach that I described and generalizing this to a very broad set of alternative to a much broader set of estimation problems. And so in fact, this relaxation that I described in the talk generalizes through a process called moment relaxation to any polynomial optimization problem. So that is any estimation problem that you can write down as an optimization problem whose data and constraints are polynomials admits a relaxation that looks similar to the one that we've used in this case. And so to me, the real takeaway message from this is that this is really a proof of concept for a much broader general approach to the construction of certifiable estimators like this for a broad swath of problems. And in fact, there's kind of like so this actually leads then to sort of a fairly natural recipe for how you might think about designing estimators like this. And so it's relatively straightforward. All you have to do is just write down your estimation problem as some kind of a polynomial optimization problem. You apply Lagrangian or moment relaxation to it to produce a semi-definite relaxation. And then exactly as we sort of argued in the talk before, what you want to argue is that this relaxation is exact in the zero noise case. And as a result, you can show via continuity then that exactness will continue to hold under sufficiently small noise. And so I do want to mention one of my colleagues in the math department, Diego Cifuentes, has put out a nice paper involving these last two steps, where he basically studies under what conditions these STP relaxations of this sort will remain exact under bounded perturbations. And so he sort of found a nice way of generalizing the argument that we used in SE-Sync via some nice algebraic geometry constraints. So he's done some of the heavy lifting for you in this case. So I'd refer you to his paper if you like algebraic geometry and are interested in this sort of thing. Yeah, and so just as an example of what one can do with this, one of the cool things about this is that since the publication of our original work on this, a bunch of folks have subsequently taken this general recipe and sort of applied it to a bunch of different problems. And so things like rotation averaging, 2B registration, sensor calibration, image segmentation, and so on, have all been shown to admit certifiable estimators that are constructed according to this procedure. So just as just to give you a quick flavor of what this might look like, I'm just going to show you one quick slide on some recent work that I've done with some very intelligent students at MIT on distributed SLAM. So we've shown recently in a TRO paper that's coming out soon that you can actually take this SE-Sync approach and apply it to distributed optimization. And so the main idea is that we show how you can modify that this relaxation that we developed on earlier in the talk to be a sparse equivalent formulation, which can then be solved in a distributed fashion or decentralized fashion using the distributed version of the Riemannian staircase. So we show how you can solve this we show how you can run the Riemannian staircase in a distributed fashion using a distributed Riemannian block coordinate descent method, and how you can do distributed solution verification using an accelerated power method to compute a minimum eigenvalue for that certificate matrix. And so the result then is that this actually gives you then the first certifiably correct distributed system, which is particularly relevant if you think about, when I have multiple robots meeting, for example, who may not have a common frame of reference, the idea to be able to arrive at a globally optimal solution in that case without assuming that you have a good initialization is particularly relevant in that case. So we think that this is a particularly useful thing to be able to do for multi-agent systems or for large scale, like city scale mapping, for instance. So let me skip over some of these then, just in the interest of time, and sort of just wrap up here. So the main takeaway that I wanted to leave you with for the talk was just that convex relaxation then provides a powerful approach for building fast and reliable machine perception systems. So we showed that this is capable of, in many instances, provably recovering globally optimal solutions under reasonable operational conditions. And in many cases, it can preserve the speed of state-of-the-art techniques if you're sufficiently clever about how you design the optimization method. So in particular, in this talk, I spent a lot of time talking about SE-Sync as a particular example of this class of techniques. But of course, we also showed just a moment ago how one can apply this to then a whole bunch of different things. And so this is currently a very active area of research. There's a lot of work being done right now. Very interesting open questions on how you should generalize this to other kinds of problems, how you can design more flexible semi-definite optimizers, how we can generate a priori probabilistic guarantees for all these things. So lots of interesting questions remain to be answered here. All the stuff that I talked about here, all the papers I mentioned are available on my website. And last thing I want to mention, some of my collaborators and I actually just had a recent survey article that in fact just posted yesterday that talks exactly about this stuff. So if any of this stuff is interesting to you, certifiable perception seems like the sort of thing that you might want to find out more about. I would encourage you to check out this survey article that's linked at the bottom of the slide here. So thanks very much. Sorry, I ran a few minutes over, but I'd be happy to take any other questions you might have.
Thanks a lot, David. All right. Questions, somebody? That's very, very nice. Any questions? We have some time. All right. So with that, let's thank Dave again. Thank you very much, Dave, for spending the time with us here. And
yeah, thanks for the invitation.
We continue to personal meetings then, Dave, the same link. Okay. So thanks, everybody. Thanks.
Thank you.
Thanks, Dave.